Since the beginning of culture, civilizations have tried to understand how the universe came into being and what it's made of. This is the basis of much of the myth and religion. Nowadays, science, in a sense, has replaced myth and religion, and it is the modern way of asking how the universe began. And some of the ideas in science sound almost as weird as ancient religions. And in particular, one of the most exciting current ideas suggests that the universe, the whole universe, and the matter inside it, is made of string.
Yes, string, but not common supermarket string. The strings which fascinate scientists today are called superstrings. If they exist at all, they will be so small that no microscope will ever be able to see them. And yet, if they do exist, they will be fundamental to the way the universe is constructed, that everything, including empty space, will have to be made from superstrings. Some physicists believe that the superstring theory may shed light on a few of the most important questions in science, including a description of how the universe was created.
Who knows if superstrings live up to their expectations? We might actually have in place a mathematical formula or scheme, something you can wear on your T-shirt, perhaps, that will capture the whole of reality at this reductionistic level. And in one sense, that would be the scientific creation myth. That would be creation. That would be all of the entities that exist, space, time, the particles of matter, even an account of how the universe came into being. We'd have everything encapsulated in a single scheme, a single principle. I'm sure that we wouldn't know why that particular principle is the one that, as it were, takes on wings and flies, rather than some other, but we would surely have there the modern version of the creation. I think there's no doubt about that.
The conventional version of creation suggests that our universe popped into existence about 15 billion years ago. But as it expanded, it cooled. And as it cooled, a host of exotic particles of matter were created, many of which only existed fleetingly before vanishing forever. Slowly, under the relentless force of gravity, those particles began to clump together into what would become galaxies. Within those galaxies, suns were born. About 4.5 billion years ago, a blob of iron, silicon, carbon, hydrogen, and oxygen that would one day be called Earth began to form from the interstellar dust in orbit around a small star. For countless millennia, that star bathed the little planet in just enough light and just enough warmth to trigger an extraordinary and possibly unique chemical miracle. A chemical miracle called life. A miracle created from stardust. Over time, the planet witnessed yet another possibly unique chemical miracle. Some of the creatures that were evolving here began to think and to question. What was it all about? What was going on? Among the diversity and variety which surrounded them, nothing seemed permanent. Everything was constantly changing. And yet, if there were any Neanderthal scientists, they would also have noticed that there are patterns in the way nature operates, that there are cycles which could be exploited for their survival, cycles in which the sun, moon, and stars seem to play a crucial role. And like the scientists who would one day follow, Neanderthal professors may well have wondered whether there are some underlying principles or fundamental laws governing the way the universe works. Not surprisingly, after so many dawns and sunsets, one conclusion mankind made was that the Earth was obviously at the center of the celestial web, at the center of the universe, and that the sun, moon, and stars were almost certainly orbiting gods. Given the unremitting evidence of the data available to them, this wasn't such a stupid interpretation of the way the heavens worked.
Well, the idea that the sun might actually go around the Earth rather than the Earth going around the sun is not at all stupid. In fact, the theoretical predictions around the time when Copernicus was working on his new theory of that old model fit the observations actually pretty well. And Copernicus's model, where he put the sun at the center of the solar system and all the planets moving in circular orbits around it, when he tried to calculate where the positions of the planets ought to be on the sky, he actually got a hopeless fit with the observations. It was only when Kepler came along in the next century and decided that the orbits of the planets had to be elliptical and not circular that we actually got a model or a theory that fit the observations.
At the time, Copernicus and Kepler's idea that the sun might be at the center of the solar system with the planets in orbit around it was a serious challenge to many deeply held religious assumptions about the universe and man's place in it. In 1604, an Italian mathematician called Galileo devised a proof for the idea, and a few years later checked his calculations using a new invention called a telescope. He was arrested and found guilty of heresy. The debate raged throughout the early 17th century, but in 1642, the year that Galileo died, a young Englishman called Isaac Newton was born.
Up to the time of Newton, the way in which science had been pursued was very different from the way in which we think of science today. In some sense, Newton can be thought of as the first experimental scientist. He realized that by observing the way things were in different places, and even in different regions of the universe, you might understand some universal principles which all objects obeyed. The most notable of these, of course, is that he discovered the way in which the force of gravity acts. And he realized that the same force that is responsible for the way objects fall to Earth is also the force that holds the planets in motion around the sun. And this was a huge advance in the way we think about the world.
Newton's mathematical model of the universe was not only astoundingly elegant, but it was powerfully predictive too. It was literally a clockwork universe, and with it, he had a means of calculating the positions of the planets far into the future. Newton had found what all theoreticians seek, an underlying principle which unifies a variety of different natural phenomena. It's a quest which has haunted all of the giants of science since Newton. As the 19th century drew to a close, the new insights into the laws of physics which men like Faraday and Maxwell were achieving seemed to be reflected in the ever more inventive technologies of the Industrial Revolution. It seemed science and technology could answer any question, solve any problem. In 1880, the chief of the Prussian Patent Office even declared that everything that would ever be invented had already been invented. The thought found an echo in America when the noted physicist Albert Michelson wrote,
"The more important fundamental laws and facts of physical science have all been discovered."
But even as Michelson was penning those immortal words amid the exuberant celebrations that attended the dawn of the 20th century, a fatal arrow was being aimed at the very heart of classical Newtonian physics. A number of theorists were beginning to notice that Maxwell's laws of electromagnetism and Newton's laws of motion just didn't seem to fit together. A German mathematician called Albert Einstein was about to enter the picture with a radical solution to the problem.
Newton's view of space and time is what I think you would say was most normal people's view of space and time. We're all conscious of living in a space which is three dimensions. You have to go in three directions to specify where you are. And we're all conscious of the march of time. What Einstein did was to really overthrow that picture entirely. He said, no, you can't think of reality like that. It's not that really we live in a space and things change in a universal time, which was Newton's idea, but rather space and time are locked together in some way.
Excuse me, sir. Do you happen to know what time Oxford stops at this train?
Right away.
It's extremely doubtful whether Albert Einstein ever uttered those often quoted words, although if he had, it was not a simple slip of the tongue. He believed that it was as logical to ask what time Oxford would stop at the train as it was to ask what time the train would stop at Oxford. He suggested that you couldn't tell whether it was the train that was remaining stationary while the track moved underneath it, or whether it was the track that was stationary while the train moved along it. It was all relative, and the concepts that Einstein produced came to be known as relativity theory. Now, relativity theory has a number of very curious consequences. For example, the speed of light turns out to be constant whenever and wherever you measure it, and yet both space and time are not. Energy and matter are also closely related to each other. Einstein also completely vindicated Maxwell's earlier ideas, showing that Newton, while not exactly wrong, was only approximately right. Einstein said there are tiny but significant errors in the classical Newtonian way of thinking about space and time.
Einstein's theory agrees with Newton's theory quantitatively under almost all circumstances. The deviations are really rather small and difficult to achieve. And so you might think, well, what's the big deal? You know, why is it such a revolutionary thing? The two theories agree for most of the time. And the answer is that Einstein had really swept away the entire conceptual scheme that Newton had. Prior to Einstein, space and time were really just parts of philosophy. They weren't part of physics. They were there as a backdrop. But after Einstein, space and time became part of physics, and it then became important to understand how they change and move and how the affairs of space and time interweave with the affairs of matter.
But as scientists and philosophers struggled with the apparently trivial but actually profound observation that time and space are somehow woven into the fabric of the universe, Einstein was wondering whether there wasn't some other, deeper truth staring him in the face. How was it that space and time were members of the cast rather than simply the stage on which the drama was being played out? And how are the stars and galaxies that populate the heavens affected by such new ideas? The unexpected answer was that all matter causes dents in the fabric of space-time. The larger the object, the larger the dent. It was a geometrical theory of gravity which worked. Time and time again, its predictions were borne out by observation and experiment. It was a theory which predicted black holes and galactic clusters, a theory of gravitation that was as elegant as it was powerful. It was a picture of the universe that wove matter, time, space, and energy irreversibly together in a tapestry of theory that came to be known as general relativity.
General relativity is a beautiful theory that has been well tested and explains many features of cosmology, the motions of galaxies, the expansion of the universe, and other phenomena. However, it has nothing to say about microscopic physics at the atomic or subatomic level. Now, it's intriguing that Einstein developed general relativity at about the same time that other people were beginning to understand the laws that govern the behavior of matter at these most microscopic scales. And eventually, this gave birth to the idea of quantum theory.
The word quantum means a parcel or packet, and quantum theory is a description of nature based on tiny packets of matter and energy. Light can be described in these terms. The packets are called photons, which stream out of any radiant object like a light bulb. But there is a problem with light. It can also be described in terms of waves of energy radiating from the source like ripples on a pond. So what is light made of? Waves or particles? An experiment was devised by Albert Michelson, who 20 years earlier said that there was nothing left to discover in science. Quite simply, it splits a beam of light, in this case a laser, into two, and sends one beam to the left and the other beam to the right. A little further on, the beams are brought together again, and the result is photographed. According to the wave theory of light, the two beams will create a pattern of bright and dark patches, what are called interference patterns, where the peaks and troughs of the light waves either add up or cancel each other out. In the Michelson experiment, this is exactly what happens. A camera placed at the end of the laser path does see interference bands of light and dark. But there's a profound philosophical hitch in the Michelson interferometer experiment, as Professor Chris Isham explains.
Well, the basic idea is very simple, that you have a light source that you split off into two beams and then recombine so that they interfere. And that's a perfectly normal demonstration, actually, of the wave nature of light. Indeed, it was precisely through that sort of experiment that the notion that light was a wave first came into place. Now, the interesting thing, however, occurs when you turn down the amplitude of the light, make it weaker and weaker. Now, according to classical physics, all that should happen is that the image will get dimmer and dimmer and dimmer. But in fact, what happens, if you look at it carefully, is you'll see it doesn't just get dimmer, it breaks up into dots. And those dots, each one of those dots is in fact the effect of a single photon. So what you begin to see is how this apparent interference pattern is made up of individual photons. In terms of quantum mechanics, one says, well, why that's happening is that what is really going through this equipment is not so much a light wave, which would be the classical view, but a probability wave, if you wish. And what is happening, the probability waves are interfering. Now, this, of course, is a very difficult thing to think about, but it's what the mathematics suggests. And then, when the probability waves peak up together, they say there's a high probability you'll get a particle there, and when they, of course, cancel out, they say there's a low probability. And therefore, what should happen, according to the theory, is you'll get speckles appearing on the pattern. Lots of speckles where the bright band was, and not very many speckles where the dark was. And in fact, that's what you see. If you look at the screen, you'll see that's what happened. Now, that in itself is not that remarkable until you start asking, how does it come about that each individual photon, as it were, knows what to do? And the only way you can explain this is that by saying, in some sense, the photon itself splits, whereas classically the light beam split. You now have to somehow get hold of this idea that the photon is somehow aware of both paths. This is a very, very strange concept.
One of the most fundamental paradoxes in quantum theory springs from the way atoms, the very building blocks of matter, are constructed. This is an atom of iron. Quantum theory suggests that the particles that make up this atom live in a curious maybe world. They may be here, they may be there. There is a fundamental uncertainty about them, which seems to defy normal notions of reality. It's an idea which has come to be known as the uncertainty principle. One of the authors of quantum theory, Erwin Schrödinger, wondered what would happen if you used an uncertain subatomic quantum event, like radioactive decay, to determine the outcome of a large-scale, everyday experiment.
Now, when you open the box, according to conventional quantum theory, what will happen is you will either see the cat dead or alive. And at that precise instant, in some way which has never really been explained, the state of the cat changes. It really becomes dead or really becomes alive. So before you open the box, before you make the measurement, all you can say is that the cat is potentially dead or alive, but you can't say which. And in fact, it would be wrong to say it is either dead or alive. That is actually incorrect. It really is in some sort of strange twilight state between these two. You open the box, you make the measurement, the cat, as it were, flops into a state of deadness or a state of aliveness.
Now, of course, Schrödinger never actually carried out this experiment in real life, but its value as an imaginary experiment is that it highlights what appears to be a key paradox in quantum mechanics. It's complete nonsense for a cat to be described as being both dead and alive at the same time. And there have been various attempts to find alternative interpretations of the quantum theory over the years. And in one such interpretation, the many worlds interpretation, there are parallel universes. In one of these universes, the cat is alive, and in another universe, it's dead. And it's only when we open the box that we discover which of these two universes we are living in.
The idea of many worlds of parallel universes has been very attractive to people perplexed by quantum theory. The notion is that there are an infinite number of universes unfolding in parallel with ours. Some are subtly different, while others are radically different. And every time we make a decision or a choice in our universe, we determine which of these parallel universes we are about to enter. But can this sort of make-it-up-as-you-go-along theory really be true? A theory in which light can be waves or particles, or both at the same time. A theory of uncertainty and probability. A theory in which the particles that make up atoms aren't really there. A theory which seems to imply an infinity of parallel universes in conflict with ours. Can it really be a sensible description of nature, the nature we see? Can quantum mechanics possibly be true?
Quantum mechanics is by no means something that's very esoteric and has no effect on our everyday experience. Perhaps 25% of the gross national product of every country depends upon the laws of quantum mechanics. Transistors, lasers, all modern electronics works upon the laws of quantum mechanics.
Well, your television camera is a classic example of it working, of course. It's stacked full of solid-state electronics, and that works entirely on quantum mechanics. Every time anybody turns on a television these days or a radio set, they're seeing quantum mechanics at work. Modern computers are entirely based on quantum mechanical devices. And in fact, in that sense, in a real sort of practical electronics, quantum mechanics has been verified millions of times, or thousands of millions of times. So at that level, quantum mechanics is fine. It tells you what happens on the average, what the probability is of certain things happening. And if you just accept it at that level, there's no difficulty. The problems only arise when you start asking, what does it mean about reality itself? What picture does it give us of reality?
The pictures of quantum reality are taken here at the European Particle Physics Laboratory in Geneva, known in the trade as CERN, for Center for Nuclear Research. This is where they probe into the heart of matter. This is where they smash atoms in order to discover how they're made. As the bits of these collisions fly apart, they leave tracks which the particle physicists can analyze and interpret, giving them clues about how the universe began.
The idea of the accelerator is essentially, it's like a big, incredibly powerful microscope, and it's looking into the constituents of the particles inside the nucleus of the atom. Well, high-energy particle physics today is sort of the natural continuation of the historical idea that we should look inside of objects to see what they're made of, so that we build microscopes to peer inside of objects, and then we discover that they're made of atoms, and then we discover the atom is made of a nucleus with electrons going around, and then we can discover what the nucleus is made of by, for example, smashing things into the nucleus and breaking it up. Now, the nucleus is made of particles, like the protons and neutrons, and these particles are the objects which are used, if you like, in accelerators like the ones at CERN, and these particles are smashed into each other to see what they are made of.
It's a sort of terrestrial astrophysics. The processes that occurred in suns billions of years ago are being recreated here on Earth. The energies involved are inconceivable, the forces unimaginable. It's a quest which reaches back in time to moments which were unbelievably ferocious. A quest which unites cosmologists and physicists in their search for the ultimate answer. In much the same way that particle accelerators are time microscopes, observatories are time telescopes. Gazing out at the heavens, they capture views of history. ancient history. Some of the light that reaches us today was first released before our solar system was born. Some of the light began its journey back at the beginning of time, but then so did we. Look deep into an astronomer's eye, and you will find blood vessels, and in those blood vessels you will find blood cells, and in those blood cells you will find molecules of hemoglobin. Inside those molecules, you'll find one of the most extraordinary atoms in the universe, an iron atom. This atom has had a remarkable life. Its life dates back to the beginning of the universe, to the moment of creation. Before it became bound up in an astronomer's bloodstream, this iron atom was part of a continental shelf. This was a geologic formation that erupted from the volcanic chaos that was the early Earth. Prior to that, it had been the gravitational field of the newborn Earth which had drawn our atom towards the planet as it drifted through interstellar space. But this was an atom which had been places, seen things. Ours was not the first sun system it had visited. Before being drawn to the solar disk that had created the Earth, it had been drifting through space. If we track our iron atom back through time, we'll get a glimpse of how it and the universe were created. As we go back in time, we begin to see it's an atom which has experienced stardom in a big way. Here's an atom which was created inside one of the biggest bangs there is, a supernova. When our universe was only 5 billion years old, our atom burst from an exploding supernova, and as we track it back in time, we can see how it came into being. Deep within the star, numerous collisions welded the nucleus of the iron atom together, and now, as we roll back the clock, we can see the components which created it. Further inside the star, it's clear that our complex iron atom was actually built from a host of simpler atomic constituents. And going back even further in time, we can see that everything is made from the simplest possible elements, hydrogen and helium. The universe is now just 4 billion years old, and gravity is about to release its grip on this early star. The iron atom has melted into the nuclear soup from which it came. And now, as we race further back in time, the earliest stars go out, and the universe becomes a seething mass of gas. It's getting hot. With no iron atoms left, we'll transfer and ride on a hydrogen atom. The universe is now just 2 billion years old, and all there is hot hydrogen and helium gas. The effect of gravity is being slowly undone, and by the time the universe is a mere 300,000 years old, all that seems to be left is a ball of hot goo. As we travel back to when the universe was 1/100th of a second old, it's getting very dense, and the electrons are behaving strangely. They are beginning to smash into the neutrons and protons, and when they do, something curious is happening. The protons are becoming neutrons, and neutrons are becoming protons. As we travel back past 1,000th of a second, the temperature hits 1 trillion degrees. Yet further back in time, when the universe was just 1/1,000,000th of a second old, we can begin to see that even our fundamental protons and neutrons are made from smaller bits called quarks. And it's the nature of the quarks which accounts for the strange behavior of the neutrons and protons. As we journey back in time to when the universe was 1/1000,000th of a second old, all we can see is a rapidly contracting cauldron of quarks. Finally, by 1 trillionth of a second after the Big Bang, we arrive at a universe so compressed that it would all fit within the orbit of the Earth and would have been 1,000 trillion degrees. By 1 trillionth of a second after the Big Bang, everything in the universe would have melted back into a soup of quarks and electrons, all obeying the 3 fundamental forces of nature. And yet there's a problem with this picture of the origin of the universe. It doesn't account for gravity. Every time the physicists try to build this most fundamental force into their equations, what do they get? Infinity.
We don't know whether these infinities that arise in physics are a fundamental flaw in physics, or if that's just the way nature works. Some physicists feel that any theory that has infinity in it has to be sick and is not a complete theory.
Modern physics is based upon the twin pillars of the theory of relativity, on the one hand, that's a theory of space and time, and quantum physics, on the other hand, that's a theory of matter. And much of what we have around us in the sense of technology or advanced experiment stems from one or other of these theories, or the 2 theories together. Now, the difficulty is this, that mathematically, when you try to marry these 2 theories and have a unified theory of relativistic quantum mechanics, then you run into difficulties. And it's particularly acute if you go to the so-called general theory of relativity, which is a theory of gravitation. You try to put gravitation together with quantum physics, and the 2 just don't want to go together. What you get is essentially nonsense. You get these infinities popping up all over the place, destroying the predictive power of the theory. So what do you conclude from that? Well, I guess you have to conclude that either one or the other or both are wrong.
Which is where superstrings come in. If they exist at all, every quark, every electron, and even the forces between them will be made from tiny vibrating strings, which can join up and reform into all the particles known to physics. And the way they vibrate will determine what they are. Physicists are optimistic about superstrings because they appear to obey the laws of quantum theory, while at the same time conforming to the principles of general relativity too. And at last, here's a theory which not only explains gravity, it actually predicts it. But it's even more curious than that. Space and time will be made of string too. The only problem is, it will never be possible to see them. They're just too small.
Well, according to superstring theory, the fundamental particles are literally string-like extended objects, but of an incredibly small size. Just to get an idea of how small I mean, they are as small compared to the size of the nucleus of an atom as the nucleus is compared to the size of the sun, for example. So that we're talking about physics at incredibly short distances.
And we're also talking about objects which appear to exist in no less than 10 dimensions. The 4 of space and time, which we're familiar with, and 6 more at subatomic levels. 10 dimensions can't be shown on television. So instead, imagine a 2-dimensional world where only edges can be seen. Into that two-dimensional world comes an object that exists in 3 dimensions. At first, it's impossible to tell what these alien shapes represent. Are they connected? Is there a pattern here? The inhabitants of the two-dimensional world might never know what's invading their lives. And yet, to those familiar with a 3rd dimension, it's readily apparent what the object is, once we're permitted to see that extra dimension. This is true with superstrings. What physics sees as separate particles are simply different manifestations of objects poking through into our universe from their own multidimensional space. But can something as simple as vibrating string seriously provide us with a theory of everything?
What I think is new about the present ideas is that they're more than just hand-waving, they're more than just a good idea. They are a detailed technical theory. If we take something like superstrings as the best example of something we have, this is not just an attempt to write a catalogue or a shopping list of entities. You've got atoms of this type, particles of that type, you've got space and you've got time, you've got various fields and so on. Let's sort of collect them all together and say that's the theory of everything. It is something which interweaves all of these entities. It's something which combines space, time, the forces of nature, the particles of nature, the whole caboodle together in a single, all-embracing, one hopes self-consistent mathematical scheme. That's what's new. It is a theory of totally everything, not just a sort of ragbag of things put together and saying, you know, that's all that there is.
If strings are the correct description of nature, then any attempt to understand the origin of the universe without taking into account the stringiness of nature is doomed to failure. If strings are the correct theory, it would change how we view the origin of the universe and necessarily the subsequent evolution of the universe.
We as physicists have a rather limited viewpoint on the universe, and we would like to explain certain specific facts in an elegant and economical way. And our hope is that we can explain all of those facts, the forces that we know of and the particles we know of, in terms of a single underlying principle. That principle is what we would then call the theory of everything. But of course, it almost certainly will not be everything. The history of science is full of lessons which indicate that just when physicists think they have a theory that explains everything, they discover there's an absolute crisis in their subject. And there are many phenomena that they hadn't noticed before which need explanation.
It may be that there is an absolute limit to what science can know. A moment so far back in time that even superstring theory may not be able to describe what was going on. At the time, the entire universe would have been smaller even than a superstring, and at such dimensions, physics encounters a barrier so impassable that we cannot know what happens beyond it. The fact that we can see as far as we do is a tribute to these giants of physics whose insight has given us such hindsight. But nevertheless, our journey back in time stops here.
It's a place where you might most expect to encounter God, so to speak. Because until recently, it was not possible to account for how the universe came into being without having some sort of supernatural input. So I think there's been a lot of attention given to this sort of creation event, as it's sometimes called. But one of the remarkable things that's come out of very recent work in quantum gravity and applying quantum theory to the universe as a whole is that you actually don't need to have a supernatural button-pushing creator back at the beginning to set the whole show going. It's possible to have the universe, so to speak, pop into existence on its own, entirely spontaneously, entirely uncaused, and entirely in accordance with the laws of physics.
But even if the superstring theory does turn out to be a description of all of space and all of time, and all of the matter in it, it's still hard to imagine that the majestic complexity of the universe we see around us may be no more than a quantum hiccup. It all seems to have been so exquisitely well designed, and yet the uncertainty principle clearly indicates that it could all be a huge unplanned accident. A freak event that had no cause and fulfills no purpose. Just one of the infinity of universes popping into existence. Just an idea which strikes at the foundations of mankind's self-esteem and, of course, his religious beliefs. This is a description of those creations which don't need a creator. There are those, however, who suggest that someone or something had to devise the rules of nature, the laws of physics, and that God, whatever God is a mathematician.